to have Dr. Michelle Guittard. She's a postdoctoral research scientist in the Biology and Paleoenvironment Division at the Lamont Doherty Earth Observatory at Columbia University. She earned her PhD from the University of South Florida College of Marine Science, where she studied interactions between ocean and the East Antarctic Ice Sheet. And she's the recipient of the NSF Office of Polar Programs Postdoctoral Research Fellowship. So as you can see, she'll be talking about late Quaternary marine-based East Antarctic Ice Sheet evolution from a sedimentary perspective. So we're glad to have Michelle here.
Thank you. Thank you for the introduction. Like Patrick said, my name is Michelle Guittard. I'm a postdoc here at Lamont. Some of you might have caught the fact that I won't actually be talking about the stuff that I'm doing at Lamont because the stuff I will be presenting today, which was my PhD work, or a couple chapters of my PhD work, I think is more closely related to sea level than perhaps what I'm doing at Lamont now. So what I'm doing at Lamont is actually a sea surface temperature reconstruction from the Scotia Sea, the South Atlantic, and I'm using TEX 86. I'll talk a little bit about that today as well. But that is dealing with deeper time, looking at a sea surface temperature reconstructions throughout the Quaternary. And today, or since the start of the Pleistocene, but today I'm going to focus on only the very near past, I guess near to us geologists, right? So I'll be focusing on the Holocene and the deglaciation and all the way to MIS, part of MIS 3, so the last glaciation. And I'm going to be talking about outlet glaciers in East Antarctica and looking at the changes in those glaciers and perhaps the forcing factors that are associated with them. And I'll be talking about this from a sedimentary perspective because I deal with sediment cores. So this is, I'm at Columbia now, but this is all work that I did at South Florida. Oops. There we go. Just some acknowledgements for my collaborators, as well as advisors, captain and crew of the MVP 0101 cruise. This is where this sediment was collected, as well as my funding. And the rundown of the talk is as follows. We're going to try to understand, or start with an introduction about understanding Antarctica, past, present, and future, but we're not necessarily going to talk about that Antarctica in that order. Then we'll discuss the challenges associated with Antarctic paleoceanography, which is what I do. I'm a paleoceanographer, masquerading as a geologist. And then we'll talk about a couple of the chapters, deglacial Holocene, sea surface temperature, and more broadly, paleo-environmental change in Svenner Channel in Prydz Bay, East Antarctica. And that's associated, this all broadly kind of deals with the Lambert Glacier-Amery Ice Shelf system. So we'll look at the Holocene, and the next bit we'll be looking at the same system during the last glaciation and looking at millennial scale variations. So let's get started. The East Antarctic Ice Sheet, EAIS for short, contains 53 meters of sea level equivalent ice, meaning if you melted all that ice, that's how much sea level would rise. Of that 53 meters, 19 meters, or about 62 feet, is contained in marine-based catchments of East Antarctica. And you can see, associated, this figures from Fretwell 2013, the blue colors are associated with submarine catchments. So you can see that there's quite a bit. Of course, West Antarctica really stands out, but you can see that there are substantial portions of East Antarctica that are submarine, and therefore their ice is grounded below sea level. That pinning point on the land is located below sea level. So you can see quite a bit here in the Wilkes and Aurora subglacial basins, as well as the Lambert catchment, and some of these catchments associated with the Ronnie-Filchner. Now, modern observations indicate that basal melt of marine-based outlet glaciers actually coincides with the presence of warm water, and the highest magnitudes, the highest rates and magnitudes of thinning coincide with warm water presence, of course. Again, West Antarctica really jumps out at us, and for good reason. You can see, this discharge and this mass loss, and it's associated with these relatively warm waters creeping up into the margin. But you'll also see that there are significant portions of East Antarctica as well, here in the specifically the Pacific sector, and I'm zooming in here on the Aurora subglacial basin, that are associated with warm water presence as well. And this is mass loss over the last 40 years. Now, this substantial loss is projected in marine-based East Antarctic ice sheet catchments, and of course, this has implications for global sea level. This is a paper by Nick Gollage and colleagues, came out in 2019. You can see by the year 2100, there is substantial, decrease in the net mass balance, as well as potential for basal melting, as well as just dynamic mass balance, which is essentially calving. So there are, and of course these, again, coincide with the presence, or they correspond to these kind of low-lying submarine portions of the East Antarctic ice sheet. And so understanding past marine-based ice sheet response is going to be important for predicting future East Antarctic stability. And we can look back at a couple, there are analogs throughout our geologic history that provide the context for, what Antarctica is doing. And what I'm focusing on today is the Lake Quaternary. So the last 40,000 years. The Lake Quaternary encompasses roughly the last 125, but I'm going to be focusing on the last 40,000. So the last glaciation through the Holocene. So Lake Quaternary paleo reconstructions indicate that Antarctic ice mass loss, that it coincides with these suborbital climate fluctuations. This is a figure from the Waste Divide members 2013, and you can see that these East Antarctic ice cores are recording these millennial scale events in the record, with some significant warming occurring kind of at the coldest part of the recent geologic past. Of course, these correspond to the Danskar events that we see in the Northern Hemisphere. And this instability of marine-based, oh, sorry, I skipped ahead. We can see that there are instabilities that are recorded in integrated records. So this is a record taken from the Scotia Sea. This is a paper that came out from Mike Weber and colleagues in 2014. These are not the same scales, but what I wanted to show was that there are these pulses of IRD that come out into the Scotia Sea, and they provide sort of an integrated record of Antarctic ice mass loss. And while this is very useful and really a great way to use this IRD, to use this data, it provides us an integrated record and doesn't give us any information. Well, it does, but just looking at the IRD record itself doesn't give us any information about the sources of that loss, or the kind of the timing of that loss. If you look at the grains and kind of use other methods, you can tell where these grains are coming from. But if you want to know if you want to know about the vulnerability of individual outlet glaciers and the forcing factors behind that, you have to go to the source. You have to go to an ice-proximal record. So the question kind of driving this research is, what is the timing and response of marine-based East Antarctic ice sheet sectors to climate forcing during the Lake Quaternary? And the approach is as follows. I'll be looking at ice-proximal marine records. So marine-based systems are susceptible to atmospheric and oceanic forcing. Of course, atmospheric from above, from the surface of the ice shelf or the outlet glacier, and then marine-based forcing comes from below, from the ocean. And so you can have ocean temperature and sea level rise forcing this retreat. It can be susceptible a couple different ways. I'm focusing on the marine here. So you can have the erosion of your pinning point of your grounding line with warm water, which causes a step back of the ice, or you can have sea level rise physically lifting that pinning point from the grounding zone, and you can have step back that way. Either way, this grounding line retreat, the thinning and destabilization, the records at the base of that grounding line or anywhere in that subshelf environment can give you a lot of information, one about what the ice is doing, but two about what the marine environment is doing, what changes are occurring throughout the water column. So assessing marine-based glacier sensitivity requires an ice-proximal record. Of course, there are challenges with that, and we'll just jump right into the challenges associated with dealing with these records and Antarctic paleoceanography in general. So ice-proximal shelf sequence stratigraphy is inherently complicated. It mostly has to do with the fact that you have ice, this very mobile force, going back and forth across the margin and essentially bulldozing your record. So we can see this is bathymetry from the Prydz Bay region. You can see these grounding lines, and these were the limit of the last glacial advance. Seaward, you can see these megascale glacial lineations, which are clues about the way the ice was flowing and the direction it was flowing, even before the last glacial maximum. Draped over this is new sediment. So all of this is kind of, it's pretty complicated. And so, when you're getting the erosion of your record, you create you have discontinuity, you can have hiatuses, and then you can also have the delivery of old material from the continent getting mixed in with hemipelagic, diatomaceous, siliceous stuff coming from the surface. And so you're mixing your age signals. The other, and that kind of leads into the complication with dating, right? So traditionally calcium carbonate has been what we've used to traditionally date these sediments, but in the Antarctic, due to the nature of the water, it's very old, therefore it's corrosive, you have a hard time preserving calcium carbonate. And so you have to look to other methods to kind of suss out your climate signals and to kind of really zoom in on your ages. And so the geochemical signals preserved in the bulk sedimentary material can be used to address these challenges. And there have been, I guess maybe not now, they wouldn't be considered novel now, but these methods that have been developed over the last couple decades to try and maneuver around these challenges presented on the Antarctic margin. One of them is biomarkers. I'll be talking about that in terms of text. Another is Ramped PyrOx, which is ramp pyrolysis and oxidation. And that is a preparatory method used to more accurately constrain a C14 date from bulk sedimentary material. And then I'll be talking about beryllium-10, not in a dating context, but rather in a relative concentration within the sediment. So let's start with Ramped PyrOx. Ramped PyrOx exploits a range of thermochemical stabilities in bulk acid-insoluble organic matter, termed AIOM, by exposing that organic matter to a linear heat ramp. And so this allows for the separation of the young reactive carbon from pre-aged material. And so once the sample has been decarbonized and homogenized, it's put in a furnace and subject to a linear temperature ramp. And so as the temperature increases, CO2 is evolved from that sediment. It's, the carbon trapped in the sediment is turned into CO2. And once enough of it has been evolved, we're looking at about 10 to 15 micromoles of carbon. And that allows us to get the youngest age possible without blowing up our error. So you need enough material to date reliably. So once you get enough CO2, that CO2 is trapped in a little glass trap, and then the CO2 is diverted to another trap. And so the CO2 that is originally trapped, is moved along the gas line, eventually trapped in its own little glass ampule, and that is what is sent off for CO2. And so these discrete CO2 aliquots are what can be analyzed for C14. And this is highlighted really well in the next slide. This is an animation provided to me by Ryan Venturelli, assistant professor now at Colorado School of Mines. And you can see these are actual graphs, actual evolved CO2 from these Ramped PyrOx runs. And so that you can see that with the evolution, or with an increase in temperature, you get CO2 that's evolved. The amount of CO2 evolved corresponds to roughly what is very old and what's very new. So older material tends to come out a little bit later. Newer material comes out in the first part of the ramp. So you can see that, once we've taken this split, again, we're shooting for 10 to 15 micromoles of carbon. Those splits correspond, those splits can be sent off for dating, and those dates you can see are spread out throughout the age. So I don't have exact ages here, but you can see that the first split, the youngest, most reactive material, has a lower date, whereas the older stuff coming out at the higher end of the temperature ramp is much older. So if you were to mix all these up, you would get something that represents the average of these ages. And that average can be anywhere from a couple thousand to 10 or 20,000 years older than this youngest age. So what we're doing is we're providing a more accurate chronology using this bulk material. The next method I'm going to talk about is the tetraether index of 86 carbons. The archaeolipids that we're interested in are found in Thalmarchaeota, a phylum of Archaea, and these are found throughout the marine environment. They contain these molecules, these chains called glycerol dialkyl glycerol tetraethers, which is a mouthful, so we just say GDGTs. And GDGT ring abundance correlates to growth temperature. And so TEX is a ratio of that GDGT abundance measured via high performance liquid chromatography mass spectrometry. Also another mouthful, we just say HPLC. And so you can see TEX here, it's unitless, because it's a ratio. And so you can see the ratio of the abundance, and that's the abundance as it in counts on the HPLC is what we use for this equation. So you can see these correspond to these structures here, and you can see the rings pretty prominently in each of these structures. So TEX itself can't be used to constrain absolute temperature. It has to be calibrated. There are many different ways to do this, but the principle is that there are core tops taken throughout the world, and the archaeolipids are isolated from those core tops, and then the TEX ratio from that core top is related to the overlying sea surface temperature, which is derived from satellite measurements. And so a temperature calibration can be calculated from this observed correlation between modern TEX and sea surface temperature. There are many different ways to do this. The approach that I've taken for this one is a linear calibration that uses new Antarctic data collected from East Antarctica to kind of help constrain the lower end of both TEX and the sea surface temperature range. The last method I'll be talking about is Cosmogenic Brillium, again, not used for dating, but rather used as a relative marker of ice shelf cover. So permanent ice shelf cover limits beryllium flux to the seafloor. Beryllium is produced in the atmosphere, and it rains down. And when it reaches the surface of the Earth, the presence of an ice shelf can limit the delivery of that beryllium to the seafloor. And here's just a little animation showing that you're going to have relatively more beryllium in an open water environment versus a subshelf environment.
Michelle, we have one question in the chat. Sorry to interrupt.
Sure.
I don't know, Vivian, you want to unmute or I can.
Yes, can you hear me?
Yes,
Yeah.
I can. Thank you.
Yeah, I was just curious. You're mentioning these various methods, but I mean, I'm not quite clear as to how that's going to relate to a chronology, because in that PyrOx method, the first one you mentioned, you're separating older and younger organic matter, but how does that eventually form a chronology in your sediment core?
Thank you for the question.
And there's a second part also that relating to this. Can you use diatoms as an indicator of ice-free conditions in the sediment core?
Yes, you can. And I'll get to the second part of your question in these next couple, in these next few slides when I dive into the details of the chapters. But the PyrOx method, it separates the organic matter, but then those aliquots that have been separated, those get sent off for dating. So those dates are what are used to build the chronology. In addition to, if there's available carbonate, we will use that as well, and I will talk about that again in these next couple chapters. But it's not the separation itself. It's separating itself doesn't get the chronology, but when we take those discrete aliquots of CO2 and we send them off to be dated, that's what provides our chronology. Is that clear?
Yes. No.
Okay, thank you. Sorry, I wasn't more clear about that, and thank you for your question. So this is a perfect segue. So we're just going to jump into the deglacial Holocene sea surface temperature evolution in Spinner Channel, and we're broadly talking about the Lambert Glacier-Amery Ice Shelf system. Okay. So local deglaciation varies along the East Antarctic margin. You can see timing anywhere as early as 21,000 years, all the way up to 6,000 years. So it varies quite a bit along this margin, and that has implications for identifying an East Antarctic source for some of these meltwater pulses, or maybe constraining the forcing of sea level or other climate factors on the retreat of this region. So there's plenty to play with, plenty of questions to be asked along the East Antarctic margin, and you can see that some of this step back might have occurred during some of the coldest times in Earth's recent geologic history, whereas some of this other step back is occurring maybe during the warm Holocene, and that seems to make more sense. So that's kind of what's driving this question. Models indicate that fast-flowing East Antarctic ice sheet marine-based glaciers are sensitive both to sea level rise as well as to ocean heat flux. And so what we're going to focus on is the Lambert Glacier system, which is a fast-flowing glacier system. We know that from modern dynamics, and we know that from bathymetry seaward of this major outlet glacier system. So again, we love acronyms. There's acronyms all over the place. The Lambert Glacier-Amery Ice Shelf system, LG-AIS, is a fast-flowing outlet glacier that terminates in Prydz Bay. Basal melting in the modern system, basal melting occurs via modified circumpolar deep water, and this intrusion occurs through Spinner Channel over here to the east. This is important because these ice-ocean interactions in this area form dense shelf water, which goes on to contribute to Cape Darnley bottom water, and that eventually that is a component of Antarctic bottom water. So this region is important to global oceanography. What we're focusing on here is this JPC. Let me go back just so I can show you. JPC 24 is here, and we're zooming in a little bit here. So JPC 24, or Jumbo Piston Core 24, is a deglacial to Holocene sediment sequence. Previous studies, to get to Vivian's question, previous studies have used diatoms to provide the context for the deposition occurring in this area. And so they are an invaluable source of information to understanding, deposition all along the eastern all along the Arctic margin, never mind just the eastern Arctic margin. So, this is the temperature. The temperature record that I'm going to be discussing is always used within the context of broader, like paleo deposition, broader environmental changes. We're just trying to provide a little bit more of an absolute age or temperature range when we're looking at these changes. So, we have F Curta, which is used to reconstruct sea ice. It's a sea ice diatom. We can see that there's an increase in F Curta near the top. Cattosaurus is usually used to say something about stratification. You can see that it it tends to like new kind of meltwater environments. And then of course, magnetic susceptibility tells us a little bit about the terrigenous component. These are laminations that I counted and summed. The planar laminations are much more abundant, but then we see these rippled laminations, which have been used in other parts of the Eastern Arctic margin to say something about kind of the activity of the currents, and say something a little bit about the energetic current regimes that are occurring on Eastern Antarctica. So we do see, we see a lot of laminations in the bottom part of this record, and then they disappear in the top part of the record. So I wanted to point that out because I'll bring that up a little bit later. So what we're kind of interpreting this as is just a more energetic environment. So getting to the chronology, center channel, this JPC24 chronology incorporates both carbonate and bulk organic matter C14 ages. The C14 ages have been converted to calendar age using the updated Marine 20 calibration curve. And you can see that we've got bulk AIOM here. We have carbonate that supplements the chronology here. And then we have a couple new Ramped PyrOx ages at these transitions or to supplement an age maybe that was previously confusing. And so you have this chronology here, and what I really want to focus on is this age here. Previously, the age of this sediment below this transition, which is the transition from hemipelagic to subglacial sediment. So this represents the step back, the local deglaciation. Previously, the age of local deglaciation was an extrapolation. So the age was coming out somewhere around 11 or 12,000 years ago, but using an updated Ramped PyrOx age right at this transition, right above the subglacial transition, we get an age of 15 plus or minus 500 years. And so this is roughly coincident with Meltwater Pulse 1A, taking into account that error here. And so I think this is very compelling. It may be that it's a little bit early, but because Ramped PyrOx, there's really no way to completely exclude old material, of course, because it's an admixture. What we're doing is we're constraining it as much as possible. But it's very possible that this age actually does include a little bit of old material. So it's very possible that it could be younger. So I think this is a very compelling evidence for contribution of this major East Antarctic ice shelf, this system, to Meltwater Pulse 1A. Of course, more research needs to be done. That is speculative, but we're looking for sources, and I think looking at the terminus of these major outlet glacier systems is a good place to start looking. I'm going to zoom ahead here. This is text. I talked about this before. I'll also be using sortable silt to say something about changes throughout the water column. This is the equation converting temperature to text that I'm using for this research. And this is our record. So this is the text record. SSTs range from -0.2, -2.5, which of course is below this freezing temperature of water. There's quite a high error associated with this. This is it just has to do with the math associated with this linear calibration. So we have this range of SSTs. I would like to focus on the trend though. In the late Pleistocene, after we have that step back, you have cooler sea surface temperatures, and then we have a warming. And then right around 7, we start to see this cooling. We might have seen cooling before, and you can definitely make an argument for that, but we see this stepped cooling right around 6, and then we have a cooler late Holocene. This corresponds well to changes in the sea ice diatom assemblage. So you can see that sea ice really kind of takes off after 6, right around the time that we see this cooling here. And then we also see the increase in sortable silt has been used to say something about the speed of bottom currents, right? So if we look here, we can see that we have a stronger bottom current according to sortable silt, and this corresponds really well to this increase in both planar and rippled laminations, which of course has been used in other parts of the Antarctic margin, East Antarctic margin, to say something about bottom water energy as well. So I think this is, again, pretty compelling that we should see this kind of like this increase right around the time that we're seeing this increase in episodic bottom currents. At the same time, we're seeing this warming. And so my interpretation is that this early part here is kind of a meltwater induced stratification. It's a cool surface environment. This is, based on these Cattosaurus resting spores, which really like that meltwater stratified environment. And then we get to a more active system. There are polynyas in this area. And so what I'm interpreting this as is that there is an increase in polynya activity. And so you're going to get an increase in sinking of that water and more energetic bottom currents as it's flowing out to the west of Prydz Bay. And then as we get to the late Holocene, we see more sea ice. And so that's associated with polynyas in that area. And so more sea ice means a less active polynya, because with the polynya, you get sea ice farther out, but with sea ice closer to the margin, you're going to get a less active polynya. And that less active polynya limits this dense shelf water formation. So that's my interpretation of what this means. The biggest take-home message from this chapter is that we see this step back at 15. It's roughly coincident with Meltwater Pulse A. I think that's very compelling, and I think it deserves future research. We're able to use text paleothermometry to reconstruct sea surface temperatures in this area. That's not something that's been done before. It has been done on other places along the East Antarctic margin, but this proxy helps us at least start to attempt to put absolute temperatures, put those in the context of changes in the depositional environment that are happening and that we've seen from diatoms. And results may indicate that dense shelf water production and circulation in Spinner Channel have changed throughout the Holocene. So moving on to millennial scale variations, we're going to look a little farther back at the last glaciation. So millennial scale variability is, we saw earlier that it's occurred throughout the last, I only showed the last 60,000, but there are records that show millennial scale variability throughout the last 70,000. These are 2 records, one from the Scotia Sea, another from the South Atlantic, and there are these pulses of what is interpreted to be IRD, spaced roughly, 5,000 to 7,000 years apart. Of course, it becomes a little bit more frequent as we get into the deglaciation, and that variability, that ice mass loss, this is what this is interpreted as, is associated with these pulses in sea level. See, I told you I was going to bring it back to sea level. And so what this tells us is that there's this millennial scale ice discharge, and this ice discharge kind of coincides with changes in sea level, and this presents us with potential for East Antarctic Ice Sheet contribution to sea level, and it shows that there's a sensitivity of or there's a potential sensitivity of East Antarctica to millennial scale forcing. Again, you can't tell the source regions from this data alone. You have to go to an ice-proximal site, which is what we'll be doing. So during the last glacial maximum, there was limited advance in Prydz Bay. It was, these are the limits of last glacial maximum advance. And so this enabled for the preservation of a pre-last glacial maximum record in inner Prydz Bay. You can see kind of this bathymetry, this more detailed bathymetry overlaid over the bathymetry of Prydz Bay. And if we zoom in, you can see that JPC, again, Jimbo piston core 34 and 35 are in this deeper, more inner shelf location, and JPC 36 is seaward of that, but still located within inner Prydz Bay. These three sequences were captured on MBP 0101. They were correlated using magnetic susceptibility. JPC 34 was the most complete. I'll go back here. Was the most complete core, and so JPC 35 and 36 were correlated to this core. They were correlated using magnetic susceptibility, and this was used to create a composite depth scale, which is what we have here. So the sequence includes a repeated pattern of sandy muds and diatomaceous muds. You can see that here in the lithlog, as well as the normalized magnetic susceptibility. And to give you kind of an indication of how this shows up in the total sediment, we can see that there's these higher percentages of biogenic sediment in these diatomaceous mud units. We're calling them DM units. When put alongside diatom assemblages, you can see that there are higher abundances in these top DM units, including more, we call them POOs. That's permanent open ocean zone assemblages. And this is a combination of diatoms. And then these are sea ice diatoms. And you can see more sea ice in the higher, in the upper diatom units. And so the sequence, the age of the sequence is unknown because early dating attempts using bulk organic matter yielded inconclusive radiocarbon ages. And so again, we use Ramped PyrOx to constrain the age of these samples. These are reservoir corrected using an average for the Antarctic margin. And again, they were converted to calendar age using this marine 20 calibration curve. Because these ages, we are assuming that this is all an admixture of a lot of different things. And so instead of trying to constrain the onset of, say, diatomaceous mud unit 2, or the transition out of diatomaceous mud unit 2, we're assigning average ages. So these are the oldest, again, thinking back to the animation, these are the oldest, this is like split 5. So these are the oldest ages, and these black ones are the youngest ages. We have decent age constraint in the upper age, in the upper unit. So, and we only had one date, one Ramped PyrOx date for this unit. And that mostly has to do with the fact that these cores are now 22 years old and they are very well sampled. So if anyone's looking for an excuse to go back here, we need more of these cores. So write a proposal. So but these deeper units we have a couple different ages. So we're using the average of these younger ages to kind of say something about the average age of deposition. It's not a perfect system, but this is as close as we've ever been able to get to usable C14 dates. So when we compare these C14, these average ages, to some of these older, these are mixed carbonate ages, these are bulk ages, we can see that we already see an improvement on the age of this chronology. So applying that chronology to the sediment, again, I'm using beryllium 10. This is my beryllium 10 record. And this has been put on the age scale. So beryllium 10, the abundance, again, the abundance of beryllium indicates, oh, these should be switched. This should be negative and this should be positive. So with an increase in beryllium, you should see less ice cover, not more. And with a decrease in beryllium, you should see more ice cover. So these highs indicate a step back, or a step back of they indicate an open ocean environment, which we're interpreting as a step back of the Lambert Glacier system. You can see that they're spaced about 7,000 to 4,000 years apart. And that, although it doesn't exactly coincide with these millennial scale temperature variations that are observed in the ice core record, you can see that they're occurring about the same, at around the same time. So what this is telling us is that this major outlet glacier is responding to some type of suborbital forcing during the coldest time in Earth's recent geologic history. So, that says something about how sensitive these systems might be. Of course, there might be some, orbital sensitivity too, right? As you get an increase in both insolation and temperature, you're getting a step back, a more permanent step back of the Lambert Glacier as the wider East Antarctic margin begins to deglaciate. And so I alluded to this in the previous slide, but what I think we might be seeing is a response to Southern Hemisphere climate variability. The retreat of the Lambert Glacier is consistent with pre-LGM retreat that has been observed at other proximal East Antarctic margin sites, including the Bunger Hills, the Larsemann Hills, and the Lambert Catchment, which is just inland of the Lambert Glacier-Amery Ice Shelf system. The Lambert Glacier, or I should say the Amery Ice Shelf system, demonstrates variability on orbital, again, this kind of step back as we're seeing everything warm up, but more importantly on these millennial scales during the LGM. So this is pre-LGM step back. Not only is it pre-LGM step back, it's repeated step back during the last glacial maximum. And this millennial scale variability that we see in our record is observed throughout the Southern Hemisphere. This is Southeast Pacific. This is of course, this is the ice core record, and this is a step back from terrestrial sites. So I think what it says is that, we're seeing a very sensitive system, and that these systems should not be discounted when thinking about source regions for past sea level rise and future sea level rise. And we're already seeing that along the Pacific sector. So a quick summary of this chapter is that these Ramped PyrOx ages reveals millennial scale retreat during the last glaciation. We can use beryllium analysis alongside diatoms to indicate open water condition in inner Prydz Bay, again, during the last glacial maximum. And this, of course, has implications for marine-based East Antarctic ice sheet climate sensitivity on millennial timescales. These are my conclusions. I'll leave them up here. In the interest of time, I'll say thank you, and I invite any questions.
Thanks, Michelle. Very interesting. Do we have any questions?
Hi, this is Brad.
Oh, hi, Brad.
Michelle.
I can hear you through the wall.
I know we're adjacent opposites. What's the geochemical reason the young carbon combusts earlier when you do the ramped heating? Is it just it's more reactive carbon?
It's more reactive carbon, yeah. So the stuff that is raining out is just it's I guess what hasn't been, I think what would have already been like reacted in older stuff has been reacted. So whatever is coming in from like from the land, anything that was reactive has already been reacted, right? So all that is left is that harder to react carbon, unless it's being, subject to 800 degrees Celsius. And so what's coming in from the new stuff, it just has more stuff that can be reacted. Does that make sense?
Mm-hmm.
Yeah.
So you'd see the same spread in ages in these ramped measurements in the tropics and mid latitudes, high latitude. Or is something that's special about Antarctica that
I suspect, depending on the environment and like the depositional environment, I think you're going to have, I think it's safe to say that you would have different spreads because the stuff coming off Antarctica is so old and the ability of the ice to carry it that far without any other like new organic carbon input, like compare that to a river, right? So compare that to just even the Hudson. You might have old stuff that is being brought in from the sill, but you're also having new stuff being added, like leaves and whatever organic material is coming in off the creeks. But in Antarctica, you're just not having the addition of that new stuff that's coming in. All the addition of that new stuff is coming in from the top. So I couldn't really speak to the spread of ages in like a tropical system versus a polar system. I think a lot of it depends on the carbon that is coming in from different sources.
Thank you.
I see something in the chat. I'm having trouble getting to it. There we go. Do we see signs of a similar suborbital or millennial scale climate variability in glacier advanced retreat on the waste? I would suspect that we do. If you look at anything, I think Klaus-Dieter Hillebrand had a paper that came out in the last couple of years that can tell you a little bit more about variability of the waste. I'm trying to think of any other papers. I would say look at Klaus-Dieter Hillebrand and some of his associated collaborators to see what is happening with the waste. I also know that during the Holocene, especially in the Ross Sea, and this is new research that's being put out or has been put out by a variety of groups. Some of the names that come to mind are Phil Bart, Ruthie Halberstadt, Ryan Venturelli, Johnny Kingslake, and they're going to tell you, their papers are going to tell you both about the timing of retreat in the waste, as well as maybe the mechanisms for retreat or the style of retreat in those systems.
Okay, thank you.
Oh. Does anybody have any other questions? Okay, I'll stop sharing.
Okay, well, I guess we're almost at the hour. So, so thanks again, Michelle.
Thank you very much. And thank you for the invite. And if anybody has any questions, please reach out. My email is mguitard@ldeo.columbia.edu. And it was a pleasure talking. Thank you for inviting me.